Hello and welcome back to this video. Today we'll be looking at this question on the screen, often considered the hardest Add Math question for CSEC level. This question was found on the May-June 2012 paper, number 8A. It's a kinematics question, and based on the CSEC subject reports, a lot of people who attempted this question did not get full marks, and a lot of people also did not attempt this question. So yeah, it's a pretty difficult question by those standards. And even now, people who try to practice this question, they do tend to have difficulty. And I have definitely heard some complaints about this one, so let's get to it. Especially the third part of the question. That's where a lot of people actually find a lot of difficulty. But yeah, with that being said, if anybody would like to try to solve this question on their own, I would recommend pausing the video right here, looking at the question and trying to solve it. But if not, we will be getting straight to the solution. However, again, I do recommend that you try to solve the question first, because it might help with your understanding of the solution. But without further ado, let us begin. So, the first thing we need to do is part I of the question. So this is drawing a velocity time graph to illustrate the motion of the car. Alright, so let's see what the question tells us. So we have a car starting from rest at point A. It moves along a straight line reaching a velocity of 24 meters per second by a constant acceleration of 6 meters per second squared. The car maintains this constant velocity of 24 meters per second for 5 seconds and is then brought to rest again by a constant acceleration of -3 meters per second squared. Okay, so in order to make this graph, we're going to need to figure out the total time, and we also need the maximum velocity. But the maximum velocity is already given us in the question, so we already have that, so we can actually just go ahead and fill that in on our graph, which I have already started sketching over here. So maximum velocity is 24. So yeah, just put that right there. And so now we need to figure out some times. So what do we need to do? We need to figure out the time that it took for this acceleration to happen. So for it to go from rest to 24 meters per second. They gave us the time for the constant velocity, so we don't need to figure that out. And we also need to figure out the time that it took to decelerate back to zero at a rate of -3 meters per second squared. Okay, so let's get to doing that then. So we know that acceleration can be represented by the following formula. States final velocity v minus initial velocity u all over t, which stands for time. So using this formula, we can substitute in our value, so we can substitute 6 as our acceleration, and of course our final velocity in this case would be 24. Our initial will be 0 since we started from rest, and then that's all over t, which is what we're trying to figure out. So therefore we have 6t is equal to 24, because 24 minus 0 is obviously 24, and t is equal to 4 seconds. So this t I'm just going to call t1 for the sake of it. So that's our first time period, so we know that it took 4 seconds for it to accelerate, and it took 5 seconds at constant velocity. So now how long did it take to be brought to rest? So again, we're going to use our same acceleration formula, but this time we are going to substitute the other values. So this time our acceleration is -3 meters per second, and that's going to be equal to our final velocity this time, which is 0 since we're decelerating, minus our initial velocity, which this time is 24 because that's where we're coming from. Again, that's over t. That's negative 3t is equal to negative 24, and t is equal to 8 seconds. And this t I'm going to call t3, since that middle one over here, the 5 seconds, would actually be considered t2. Okay, so now let's fill in the information on our graph. So in order to get the time taken to get to the speed of 24 meters per second, that's just 0 plus t1, which is obviously 4. So let's just fill that in. And just put this 4 right there. And then now we need to add t2, which would be 5 seconds, to the 4. So that's going to be 4 plus 5, which is 9. So our next value that we need to add is 9. Can add that like right here. Move that up. And then now we need to add t3 to 9, which gives us 9 plus 8, which is 17. And then 17 goes over here. So that means the total time taken for our entire trip would have been 17 seconds. And now that we have our time values, we can go ahead and draw a graph. Or rather, in this case, sketch a graph. But when you're sketching a graph, remember that doesn't mean that you shouldn't use a ruler. You should definitely still use a ruler. It just means that your values don't have to be exactly accurate. Oh, I don't really like that line. Let's try that again. So let's just draw a line. So we know that we're supposed to reach 24 at 4. Let me just move this down to here. Extend this over here. So that looks neat. So that looks like it's around 24 at 4. And then now we need a horizontal line from 4 to 9. And that's going to be because the velocity here would be constant. And a constant velocity, of course, means that there's no acceleration, so the gradient should be horizontal, which means that it's obviously equal to 0. And then from 9 to 17, we're going to connect these with a decreasing line, because we're decelerating at a constant rate down to rest. So this is a sketch of our graph. Let me just add some extrapolation lines real quick, so you can kind of see what we're getting at here. So that's supposed to extrapolate to 4. This is supposed to extrapolate to 9. So yeah. And of course it ends at 17, and that time is in seconds. So that right there is part 1 of the question complete. If you would like to, you could also add a title to your graph. I think that's a nice touch, especially on your paper, but I don't believe that it's necessary, but it is a nice touch. Okay, so moving on, let's just draw another line to separate. So this is now going to separate part I from part II. So this right here was part I. This right here will be part II. Okay, so part II is talking about the total distance traveled by the car. And if you remember a velocity time graph, if you want to find the distance of whatever is moving and being graphed, then you simply can do that by finding the area under the graph. So that's because if you think about the equation for velocity, which is distance over time, you see that with a little bit of transposition, you get distance equals velocity times time. And if you're on a graph and you want to multiply the two axes, that corresponds to taking the area under the graph. Because if this was a rectangle, it would be the velocity value multiplied by a time value, which is obviously velocity times time. If it's a triangle, it's half velocity times time. So on, so forth. If it's a trapezium, it's again gonna be half a sort of velocity value times a time value. So that's how it works on a graph. If you're on a velocity time graph, the distance is equal to the area underneath the graph. So let's do that then. So for the sake of actually the third part of the question, I'm going to split this into stages. So I'm going to call this S1, which stands for stage 1. I'm going to call this S2, stands for stage 2, and S3, which stands for stage 3. So S1 is 0 to 4 seconds, that's our acceleration stage. S2 is 4 to 9 seconds, that's our constant velocity stage. And S3 is 9 to 17 seconds, which is our deceleration stage. Okay, so now we can go ahead and calculate the areas. So I'm going to call A1, which corresponds to S1. So that's our first area. That's a triangle. Formula for area of a triangle is half base times height. Then we can substitute. So our base is going to be 4 seconds. And our height is going to be 24 meters per second. And that's supposed to give you, I believe, 48. Let's just check it on the calculator. Indeed, it is 48. And this is in meters. The reason why this is in meters is because they gave you your velocity in meters per second, and they gave you your time in seconds. So if you multiply meters per second times seconds, that second value, well, the seconds value, I should say, is going to cancel, and you're going to be left with meters. Let me show you what I mean. So m over s, which is meters per second, multiplied by s, which is seconds. This corresponds to velocity times time. These two are going to cancel. You're going to be left with meters, and meters is, of course, the value that, sorry, not the value, it's the unit that measures distance. So that is why your area is going to be measured in meters in this case, because your area is actually representing a distance. So that's important to note. Okay, so now A2, corresponding to stage 2, is it's a simple rectangle, length times width. So that's just going to be length being 24, aka our velocity, and our time, which corresponds to the difference between 9 and 4. So 24 times 9 minus 4 is, of course, 24 times 5 times 5, which is 120 meters. Alright, and our final area, which is also our final distance, A3, corresponding to stage 3. Again, we have a triangle, half base times height, and that's, of course, half our base, which is 17 minus 9, times our height of 24. Also, guys, when you're doing these distance questions, try not to have a negative in there, because distance cannot be negative. So even though we're going from 9 to 17 seconds, we write the difference between them as a positive, which is, of course, 17 minus 9, because we don't want to end up with a negative distance. Because, of course, distance is a scalar, it cannot be negative. So this is, of course, half times 8 times 24. And if I put that into my calculator, 8 times 24 divided by 2, that's supposed to give me 96 meters, of course. Okay. Now the last thing we need to do is we're going to write a therefore symbol. It's three dots in a triangle. I'm going to put total distance. I'm just going to write DIST for short, is equal to 48 plus 120 plus 96, which will give me 264 meters. Let's just check that on the calculator to be sure. Yep, 264 meters. Okay, so as you can see, the first two parts of this question were relatively standard. Nobody really had a problem with these two parts, but it's the last part over here, part 3, that often gets quite confusing. So, what I'm now going to do is I'm going to find a nice little area down here. Just going to divide this again so that we know what we're working with. Right down there. Okay. Alright, so this is the space that we're going to use for part 3. We'll just label this part 3. Okay. So we have our space. Let's see what we're doing now. Alright, what does the question say? The question says, a second car moving at a constant velocity of 32 meters per second drives past point A 3 seconds after the first car left point A. So they will now want us to calculate the length of time after the first car started that the second car is going to meet it. And they give us a side note here that says, assume the cars meet during the time when the first car is moving at constant velocity. Okay, so the first thing that we can realize here is that the cars are going to meet in stage 2 on our graph. So stage 2 is when the first car is at constant velocity. So we know that it's going to meet sometime between 4 and 9 seconds, right? And let's just be sure, yep, length of time after the first car started. So the length of time after the first car started is basically saying the time from 0 seconds. Because the first car started from rest at point A, and on our graph we used that as 0 seconds, because that's when we started recording measurements of time. So basically all that's saying is the time since 0 seconds. That's what they want. Alright, next thing that we need to realize is that the second car is moving at a constant velocity of 32 meters per second. Okay, so I'm going to go ahead and actually just draw something on our graph here. So I'm going to just put this line right here, straight line because it's a constant velocity, right? And I'm going to put a label here as 32. So this 32 is telling us that the second car has a velocity of 32. And then of course that car is supposed to start 3 seconds after. Oh, that's kind of overlapping. Not so much of a fan. I'm gonna erase that. Just continue this extrapolation down to here. This is supposed to say, oh wait, I can use the text tool. So let's use the text tool and just insert a 3 right there. Yep. Okay, so that 3 is when we start recording or time, or rather when the second car drives past point A. So it drives past point A at time equals 3 seconds. So that's going to be important for when we're developing our method to solve this. Okay, so how exactly are we actually going to solve this, right? So they want a time, but the thing is, how are we going to get this time? So in order to get this time, we're going to need something that both of these cars share in common when they meet, right? We're going to need to develop some form of equation that's going to be able to be equated so we can figure out what that time is supposed to be, right? So let's think now. So what are these cars going to share if they meet at a point? And yes, they share a time in a way. They share a time since time equals 0, but that's exactly what we're trying to figure out. So how are we going to figure that out? We figure that out with whatever else they share, and whatever else they share actually turns out to be distance, right? So their distance from point A is going to be the same. Why is their distance going to be the same? Let's think about it, okay? Let's pretend that you and a friend start at the entrance of an amusement park, right? And you both want to get to a food stand that's somewhere in the park, right? So you're both gonna take different ways to get to that food stand, right? And eventually you reach to the food stand. So when you reach to the food stand, you're both in the same exact place, which means that you have, of course, met. And if you meet in that same place, then both of you have the same exact distance from the entrance, right? So you're both the same distance from the entrance. So you both share, at that point in time, the same distance. And it's the same thing with these two cars. If these two cars are going to meet and they both started from point A, then that means that when they meet, they share the same distance from point A. So that's going to be the crucial thing to solving this question, right? So now the other problem that we have is how we're going to come up with these equations to solve it. Well, if we were trying to solve for time, then we need to write a distance equation in terms of time. So let's start with the first guy, right? Let's write an equation for that. So let's look at the side note that they gave us. They gave us the side note that says the cars meet when the first car is at constant velocity. So they meet in stage 2. So if they meet in stage 2, that means that the first car must have traveled 48 meters already. Reason being is because to get to stage 2, you have to first go through stage 1. And I realized I forgot to label this back after I erased it. So let's just label that stage 1. Okay. So if the first car went through stage 1 and it is now in stage 2, it has to have traveled at least 48 meters. So we can start our distance equation. So we're going to say D1 corresponding to car 1, right? So D1 is going to be 48 plus something. And we're going to figure out this something in a second. But before I do that, let me just label these two graphs. I'm going to label this as car 1 and this one as car 2, so we know exactly what we're talking about, right? So now, how do we get that second part of our equation, right? So if we're somewhere in stage 2, what was our distance formula for stage 2? Our distance formula for stage 2 was the velocity times the time, right? So our velocity is 24, so it's going to be 24 times some time. But you'd be tempted to write 48 plus 24t. But the reason why you can't write 24 times t is because that would imply that you're actually starting at t is equal to 0. The reason being is because if I put in t equals 0 here, then I'm going to get the distance of 48. But if we look on our graph, at time equals 0, the first car hasn't started moving, so that distance has to be 0. So of course this equation cannot be correct. So what we're going to have to do is we're going to have to geometrically shift the equation over. What do I mean by shift it over? I just mean that instead of having 24t, I'm going to shift that t over 4 spaces. And in order to do that, I'm going to have to subtract 4. Let me write that 4 a little bit better. So the reason why I have to subtract 4 is because you want that distance of 48 to occur at the time is equal to 4, right? So instead of it occurring at time equals 0, which is what it would have done if we had 24t, I'm going to have to move it 4 spaces forward. But you can kind of think of this as undoing what we just did. So if I move the equation over 4 spaces, I'm going to have to subtract 4 in order for it to work. And let's test this out now. Let's see if it actually does work. So if I put in t is equal to 4 in this equation, I get a distance of 48. And if we look at our graph, we see that that's correct. when time is equal to 4, car 1 has indeed traveled 48 meters. And if I put in t is equal to 5, I'm supposed to get 48 plus 24, which of course would correspond to the distance the car has traveled through stage 1 and 1 second into stage 2. So I also need to make another important clarification, is that this equation is only valid for, I'm going to put for t is greater than or equal to 4. The reason why it's only valid for those is because we already counted any value of t before t equals 4 in our constant of 48, because that would be in stage 1. We only want values of t in stage 2. So it's important to realize that this t represents the time that starts from 0. So let me just put that as an asterisk. I'm going to just put that, let's just put it right here, asterisk t starts at 0. So there are some so there are some sources that will use t starting from 4 seconds, so they'll just put 48 plus 24t. But the problem with doing that, in my opinion, is that you're going to have to adjust the second equation to match that, right? You're going to have to adjust the t in that second equation to match that. And in my opinion, that's more difficult than just having both of them start at t equals 0 and making your adjustments from there. In my opinion, it feels more intuitive, because I'm saying that, okay, if I start 4 seconds later, I just have to subtract a 4. If I start 3 seconds later, I just have to subtract a 3. However, if you do want to just use t right here, you can head over to fastpassmaths.com. That's fastpassmaths.com. And I think they present it really nicely over there of how you would do that method. However, for this video, I'm going to stick with this method because I believe personally that it's easier. Okay, so this is our first distance equation, right? Our second distance equation is going to take a similar format. Similar velocity times time, right? Distance is velocity times time. We all know this. So for the 32 meters per second velocity, so it's going to be 32 times some form of t. But as we just talked about, this again, this car did not start at t equals 0, right? So if I was to put 32t as my equation, then that means that at t is equal to 1 second, I would have a distance of 32 meters. But of course, I haven't started. Well, we the people who are recording the distance, we wouldn't have started recording this car's distance, because this car drives past point A, which is our reference point, 3 seconds after the first car, right? So we don't know about the second car until t equals 3. So that means any value of t before t equals 3, that has to be equal to 0, no matter what. So the only way we're going to get that in an equation is if we put 32t minus 3. So the reason why that's going to work is because we've, again, done the exact same thing. We've taken the equation and we've just shifted it over to t equals 3. So now we start at t equals 3. If we put in t equals 3, then it's going to give us 0, which is accurate. If we put in t is equal to 4, it's going to give us 32, which is also accurate, because in 1 second we would have traveled 32 meters, because we're going at 32 meters per second. So again, we have to make a clarification that this is for t is greater than or equal to 3. I should write a s here, that stands for seconds, just to clarify. Okay, so now that we see how these two equations come about, all we have to do is just equate them, because we already said that the distances are equal. So if, I'm just going to write a quick if statement that says if both cars are Sorry, that's a bit too close. Both cars meet D1 is equal to D2, which is basically what we discussed earlier when we said that they must have the same distance, right? And since we now have our distance equations, we can simply just equate those. So we're going to just expand these brackets while we do that. So that's going to be 48 plus 24t minus 24 times 4, which is 96. I believe we already did that calculation. And that's going to be equal to 32t minus 32 times 3, which also happens to be 96. Okay. So now that we have that, let's just simplify this left side. So that's going to be 24t minus 48, since positive 48 minus 96 is negative 48. It's going to be 24t minus 48. That's of course equal to 32t minus 96. And then we're going to transpose, we're going to put like terms on one side. So this 24 is going to go to the right side, and this 96 is going to go to the left side. So this 24 is going to become negative, this 96 is going to become a positive. So it's going to look something like this: 96 minus 96 minus 48 is equal to 32t minus 24t. Let me just move this down a little bit so I have a bit more space. Alright. And then now we're just gonna have 48, because 96 minus 48 is 48, is equal to 8t. And then if we divide by 8 on both sides, then we can write therefore t is equal to 6 seconds. And that, my friends, is our answer. The reason why that's our answer is because we took t starting at 0 seconds, which is of course when we took the first car to leave point A. So we have answered the question, because 6 seconds is indeed the length of time after the first car started that the second car would meet it. So yeah, that's the big bad question that everybody always complains about. I understand if it's a little iffy and if you might not understand it the first time, but replay the video, or not the entire video, but that part that you didn't understand, replay it a few times, think through it. If you want, you can try think through the question on your own. And the reason why that's beneficial is because if you solve it, then hey, you solve it. But if you don't solve it, at least you would have had a mental familiarity with it, so you can come back, watch the explanation, and hopefully it will actually stick. Right? So that that's our solution. All parts. So we did part I, and part I. So that's the question. I really hope that you learned something today, or you picked up something that might be useful in your additional mathematics studies. And I want to thank you very much for watching, and I wish you all the best, and I will hopefully see you in another video. Goodbye for now.